Right, good afternoon, everyone. My name is Karthik. I lead the delivery perception team at Zipline, and today I'm excited to share all the cool stuff that we're up to on our quest to scale autonomy to every backyard. So what is Zipline? We are the largest commercial autonomous delivery system on Earth. Today, we serve 7 countries. We've flown about 115 million autonomous miles, making 1.6 million commercial deliveries over these past years. We serve about 5,000 health facilities around the clock, and we've been able to do all of this with an impeccable safety record. Over the past few years, we've been hard at work commercializing and operating Platform One. How Platform One works is, imagine you're a doctor at one of these health facilities, and you really need a vital piece of medication delivered to you. You place an order with Zipline. We send a fixed-wing aircraft that can fly up to 80 miles and parachute drop the vital supplies exactly where you need it. This system has been scaling up really quite fast in all the countries we operate in. Since 2022, we have made about 47,000 life-saving deliveries, and we're now reaching a scale in some of these countries where we can actually quantify population-level impact of our product. For example, Wharton recently published a report that shows that we are seeing a 51% reduction in maternal death rates in some of these countries that we're serving today. So as we've seen this expansion, we started with blood. We see a growing demand over the past few years for lots of different use cases. Today, we deliver not just blood, but also vaccines and HIV treatments. But we're seeing a lot of demand across different use cases, but also different geographies that made us sit back and think, what would it take to extend this experience of instant logistics to every human on Earth? So we went back to the whiteboard and started thinking about this. We have a platform that can serve any location, any facility, any home that looks like the picture on the left that can be served by a parachute. What does it take to take this experience and bring it to any home where the space might actually look a lot more like the picture on the right? We talk about this as achieving dinner plate accuracy. What does it actually take? What is that platform that gets us there? So as we thought about it, turns out 3 things really matter for our customers. Well, table stakes for drone delivery, that it has to be fast. It has to beat a 2,000-pound car making its way through traffic to get your burrito to you. The second piece that customers really care about is how loud the experience is. We wanted to build a product that seamlessly blends into the neighborhoods that we live in. And the way we do this with drones is we actually have an aircraft that stays 300 feet up in the air. So it's out of sight, out of mind. It's not something that you basically notice at all. And we lower your package from that height of 300 feet or 100 meters into your home. Finally, it's really important to make sure that this experience is safe. We wanted to build a system that your children or your pets might be happy to be around. And what this means is that we designed this delivery zip. It's this cute little robot, and that is the only thing that you interact with. You as a customer watching out your window is only going to see this. We spent a bunch of time iterating and prototyping these ideas, went through a lot of testing, and as of earlier this year, we're in commercial operations in a couple of cities in the US. Just wanted to show you what that actually looks like. So if you go to Dallas today, you can actually pull out your phone, download the Zipline app, and place an order from a nearby Walmart. A runner goes through the store, picks out the stuff that you need. Turns out that's actually the slowest part of the delivery experience. The delivery zip gets loaded with your package, which then makes its way up into the larger aircraft. The aircraft undocks, rises 300 feet into the sky, flies a straight-line path directly to your home, navigating the airspace while it's doing that, and lowers this delivery zip on a tether right into your backyard. So if you're sitting at home watching out the window, it is this literal sci-fi experience of watching your stuff fall out from the sky. And then the delivery zip goes back into the aircraft, makes its way back home, ready for the next delivery. So as you can imagine, building the system, it's a lot of moving parts, it's really complex, and lots of things go into making this operational. Way too much to cover in a 20-minute talk. So today, I'm going to focus on how we think about autonomy for the last 100 meters as we make a delivery into your home. So as we think about the backyard delivery problem, it really boils down to two things. We want to be able to deliver all the time. A customer does not care if it's windy, sunny, day or night. They want their stuff. And when we think about how this applies to a little robot that's skydiving out from 100 meters up in the air, wind becomes something you really need to think about in order to be able to achieve the dinner plate accuracy that we are striving for. This means that we needed to instrument our delivery zip with thrusters so that it can actually precisely maintain its position and fight wind as it makes its way down. This actually becomes a very interesting two-body planning and controls problem. And there's some really cool things we can do. For example, on a particularly windy day, we can actually ask the aircraft for an assist. So it can actually move the aircraft laterally and tug on the line, which helps the delivery zip fight wind a little better as it comes down. Now, the second part is we want to be able to scale this experience to every home in a neighborhood. As we started looking at the geographies of pretty much any place that we wanted to serve, what you end up seeing is that, yes, there are a few homes that look like the picture on the left, where nice open fields, relatively easy autonomy problem, but then you run into the incredible diversity and just how unstructured backyards really are. You very quickly start seeing trees, cars, pools, string lights that my team thinks a lot about, as you'll see in the upcoming slide, and also just the fact that backyards are living spaces that were designed for humans. They weren't actually designed for robots falling from the sky. And they also changed, right? People build stuff, people move stuff, and weather ends up mattering quite a bit too. Like backyards look so different in winter or fall. And this meant that we had to invest in an onboard perception stack. And why onboard? Well, the latency just doesn't close to be able to pull off a last-second maneuver to avoid a tree or a string light if you aren't doing everything onboard on the edge. So our delivery zip has a pair of stereo cameras, a fisheye camera, and we also carry infrared illumination with us so that we can light our way up as we come down into a home at night. Of course, everything runs on edge, and when you're thinking about a platform as constrained as this, there's pretty extreme size, weight, and power constraints. And of course, like to emphasize the weight, every gram we save here on the sensor suite is another gram of payload we can deliver to a customer. So that becomes incredibly important. So I wanted to spend a moment just showing you what the footage looks like when a delivery zip makes its way down. What you're seeing here is footage from our test sites. We've built up a whole suite of backyards all around the country that we can deliver to in practice. And these test sites are a unique spot where cows and drones live in a happy coexistence. And I really wish sometimes that I could ask them what their delivery experience is like, because they've experienced way more of these deliveries right now. On top left, you see something that we call the obstacle course. On the top right, I wanted to emphasize some of the key challenges, right? Why is this a hard perception problem? On a windy day when there are gusts, we are subject to really high motion as we come down. We need to solve this with rolling shutter cameras, which is a challenge in itself. We also have to handle night, like in the bottom left picture, where things come into view relatively late. And we also need to be thinking about weather. So on the right, bottom right, you see us doing cold weather testing in full snowed out conditions. And just taking this experience and scaling it is just solving incredible long tails of diversity. So as we started thinking about how to distill down, how to boil down this perception problem, turns out like there are really two things we are trying to answer. One is we want to understand the geometry of the home that we're coming into. So that answers where stuff is, but also how flat stuff is. Because turns out that a flat spot is probably a good spot to place a package. But that doesn't take care of everything. Like swimming pools is a classic example of flat things that you obviously don't want to deliver into. And that means we need to also understand the semantics, like what stuff is. And we put those two together into an output representation that's helping the planner answer two questions. What do we want to avoid, and where do we want to deliver? Our first cut at this problem was to exactly mimic this way of thinking. So we came up with a stereo network to answer the geometry problem. And it was very clear from early prototyping that we had to embrace the power of like machine learning and deep learning and state-of-the-art methods, because like that's the only way you can process high-resolution cameras and also scale with diverse data that you're going to encounter in the real world. Another little trick that we found incredibly valuable as we started productionizing this was to train the models to predict their own notion of uncertainty. Like on the bottom there, you see that the model lights up that is uncertain about reflective surfaces like the windshield, but this also really helps in textureless regions, areas of low visibility, night, or even high motion. And it's really useful to communicate that information. We also came up with a semantic segmentation network with some architectural tweaks to make it really good on thin objects. Both of these get temporarily accumulated into a mapping stack that is then trying to estimate some score of how good a spot is to place a package in. Here is just colored in red and green, where the more red it is, the worse spot it is to place a package. So we built this system, did a lot of flywheel iteration, made it work at night, made it work in a lot of these conditions, did an extensive validation campaign, and actually deployed this in commercial operations earlier this year. As we scaled up, there were some key learnings that I wanted to share with you, so specifically 3 key insights. One is that stereo and semseg are best thought of as not independent tasks. They can actually benefit each other. We found that when we are operating in textureless regions, knowing that that surface is snow actually really helps depth prediction. And just due to a vantage point of hurtling into the ground from 100 meters up, scale ambiguity becomes a big thing. Like that patch of concrete there, it's really hard to tell from one image if that's on the ground or it's actually the roof of a pergola or some other structure. It turns out it's the latter. And here's where understanding depth, understanding stereo, actually helps us identify that that's a roof, and we probably shouldn't place a package there. On the right, you see an example that's particularly tricky for us, which is wires and power lines casting shadows. There's actually only 2 wires in the bottom of that scene, but it looks like there's 4 because of the shadows cast. And here's where semantic segmentation is really good at recall. It's really good at picking out all thin objects in the scene. But in order to get your precision high, it's also useful to understand depth, or you find that you're dodging shadows all over the world as you come down, leading to a pretty degraded customer experience. Maybe to state the obvious, thin objects like clotheslines demanded that we process higher resolution just to get enough pixels on target, but also achieve lower latency. On the left there, you can see us at one of our test sites replicating a clothesline avoidance test, where the clothesline actually just comes into view with enough pixels just in the last few 100 milliseconds. And we need to be able to detect that and dodge it so that we can deliver the package. And maybe this one is the bitter lesson that's perhaps becoming increasingly obvious today in all the different spaces that you're hearing about, right? We need to make systems that evolve with data. The complexity has to be in the data pipelines. And we found this too. The difference between the stereo system on the left and the right, the sharper images versus the blobs on the left, is literally just better data and more data. And what we found was we were bottlenecked both from a compute standpoint and just a performance improvement standpoint on our mapping stack. We were just twiddling way too many parameters, threshold tuning, just wasn't reaping the benefits of the upstream improvements. And it became clear to us that we had to embrace something more data-driven. This led us to develop V2 of our perception stack that we call MapNet. It's an end-to-end learned 3D scene understanding model that is really combining all 3 insights. We directly input images and predict 3D maps containing a notion of occupancy as well as deliverability. We jointly learn semantic segmentation as well as stereo, formulating them as a multitask learning problem that gets the benefits that I just talked about. And all of this can run in a single forward pass on GPU, which means we can both achieve lower latency, but also process high-res images. That's the rough architecture of our stack. And what you can see on the left is we are making this delivery into this obstacle course. And on the right, you can see the real-time outputs from our MapNet model, where we're able to perceive the building, all the chairs, and actually realize that the best spot to deliver into is that little clearing in the middle. Here's the same example of a clothesline. And you can see that MapNet is able to identify that thin clothesline right in the last second and pull off this evasive maneuver and actually deliver this package. You see that once more. And with some iteration, we were able to get the system working at night as well. This is something we see pretty commonly at customer homes, where a tree branch on the left, you can barely see it, which is what makes it really challenging. It pops up seemingly out of nowhere, and we need to dodge it and actually place the package on the ground. And on the right, you can see the outputs of our MapNet algorithm able to do that. And we're able to do this pretty reliably at scale in operations today. So yeah, stepping back, right? I talked a lot about the models, but the real wins actually come from investments in the data pipeline. We take a 3-pronged approach here. So we have a robust data collection pipeline that leverages real data, where we can actually go out and collect diverse examples of particularly challenging scenes. We have a data collection rig instrumented with LiDAR, so we can self-supervise depth from having a fancier sensor that we can't afford on board on a production system. Of late, we've made a lot of improvements and a lot of investments applying off-board foundation models for dense 3D reconstruction from images. And because you're no longer compute constrained and can actually throw state-of-the-art stuff at it, we're able to produce these really, really rich maps that we can now use to validate our system, as well as train it. We also are able to leverage synthetic data. We've made a lot of investments in getting the right synthetic data that actually models our sensors really well. And one of the things we've learned is that geometry actually closes the sim-to-real gap really quite well. You see a lot of transfer as you can even one-shot to pretty reasonably good performance. Semantics takes a bit more work to transfer. And finally, on the third side, we leverage a lot of data augmentation techniques to make each data point count for more. As one example, here you see a descent that was collected with a relatively smooth trajectory on a non-windy day. And we can simulate the effects of high motion by just applying blur and rolling shutter augmentation. So what does it take to get something like this into the real world? We think about our safety and testing framework as a Swiss cheese model. The idea is that every layer of testing catches a different kind of failure. So it's incredibly rare for a specific failure mode to make it through all of the different holes that your testing layers might expose. And the more testing you have at each state, at each level, and the more layers you have, the rarer it is for some tests to sneak through into commercial operation. So here's the goal, right? We want to be able to deploy a fully autonomous service on day one, serving real customers in a new location. Again, there's no remote operator. This has to be completely autonomous. In order to do this, we run thousands of flight tests every day. At our test sites, we expose our system to all sorts of weather conditions well beyond the envelope that we actually operate in. But we also do lots of crazy things, like whatever could go wrong, can we test it? So here you see an operator actually yanking on the delivery zip to make sure that our system responds in the way it should. Now, flight tests, well, hardware is expensive. Flight tests are slow. So before any change actually gets out to the field, we run millions of simulations, right? These simulations can be hardware in the loop, where we fly entire missions with actual hardware on a bench. It could also be on the cloud, where we run thousands of deliveries and really expose our system to all the challenges it might encounter. And of course, this is a complicated mechanical system, so every component goes through rigorous component testing to make sure it can actually endure the hardships it might see in the wild. So putting this all together, this is what it looks like. This is an actual home we serve today in the Dallas region. Here's a customer placing an order, receiving a delivery. The aircraft is basically out of sight. It's just a few pixels in this image. We're able to dodge this string light, dodge a swimming pool, dodge some awnings and buildings, mapping everything out in real time, and actually make this delivery and make a customer happy. On the right, you can see the outputs processed. Again, everything was real time on board. You can see that we are able to identify the pool, the string light, and the buildings on our way down. Now, this isn't just one example, right? We're actually serving tens of thousands of customers today. And it might surprise you who the power users are. These aren't like people just excited to try out a demo or young folks wanting to try new technology. Our biggest power users are elderly folks who just don't want to make an extra drive, or moms with young kids who just don't have the time to do it. And putting some numbers behind this, this is what our growth curve has looked like since we launched in January. And we started commercial operations in Dallas in late in April this year. This chart is showing deliveries per day. And what I can say is today, every week we are launching a service with a new Walmart facility. And from day one, each of those facilities is serving thousands of new customers. And every one of those sites is seeing exponential growth. And you can order something like 60,000 products off of Walmart today. We're also starting to deliver food with Chipotle. And we remain committed to our healthcare angle. So we're talking to Cleveland Clinic and a bunch of other partners that we're hoping to announce soon. What I presented today was a very, very small window into all the things that go into making this a fully vertically integrated instant logistics system. We do everything from manufacturing our own planes to multi-agent planning to airspace safety to building our own apps. So if any of that is exciting to you, and you want to join us in our quest to delight customers every day, I invite you to check out our career page, and I'm obviously happy to hang around and chat more about any part of the system that you'd like to learn about. Thank you.